Okay, so thanks for coming out. Just a couple announcements before I get on to the actual core topics of the what we're going to cover today. First off, I have Alpha Sour starting this week. They didn't give me an office for the last couple of weeks because there are currently 12 contract instructors and they're trying to coordinate office space for all of them. So they finally finalized where my office is going to be. So starting this week until the end of the semester, my office will be at ENG 428 from 11 to 1 after class every Wednesday. So if you need to see me in person, either send me an email or you can schedule an appointment with the department, and I should be able to accommodate you. Also, there's some couple of practice problems posted. Had a couple of requests to release some problems, what you might expect on the midterm, or stuff that'll actually get you practice, get you going for covering the topics in this course. So I've released a couple of problem sets, and I'll try to release one every week after each class, just to get you prepared for the topics that I'm covering in this course. And then answers will be released hopefully the week after each problem set is released. And then full solutions, I'll either make a supplemental video or I'll cover them during a review session when we prepare for the midterm and the exam. All right? Okay, so we're gonna cover regression one more time in a little different aspect. It's probably be the last time we cover it until you see it on the midterm. And then we're going to get on to classification, which is probably the more useful aspect of machine learning that you probably want to know. And then we're going to get on to logistic regression, which is pretty much the classification, just in the name for it. And then we'll get on to regularization, which is the next topic of your lab. Once we finish today's lecture, you should be able to finish that part of the lab. And then I'll show you a couple more MATLAB demos, just to get you going for the machine learning stuff. Okay, so without further ado, let's get on to classification. So when we talked about regression, we talked about predicting a continuous valued output. If you want to predict housing prices, or if you want to predict whether your stocks are going to go up or down, it's a continuous valued output. Classification is a discrete. You're predicting a discrete output, yes or no, spam or non-spam, 0 or 1. You're predicting whether the output falls into a discrete set of classes instead. All right? So, predict, let's see here, discrete valued output. So the keyword is discrete. We're not going to continuous anymore. Just for the time being, we're not. Okay? So for now, what we're going to do is we're just going to concentrate on the two-class case. So yes or no, 0 or 1. We're going to consider multi-class later. Obviously, there's data sets where you can group a point into one of multiple possible groups. We're just going to take a look at the binary class, or the binary case for now, 0, 1, yes or no, and so on. Okay, so for now, concentrate on it's called the binary classification problem, which means that the input is expected to belong to one of two classes, spam or non-spam, yes or no, and so on and so forth, right? Yes, no, 0 or 1, spam and non-spam, and so on. And then we'll digress and consider the multiple stuff later. Okay, so example applications. I pretty much rattled them off the top of my head. Okay, so we've got email, right? Spam or non-spam. Or let's say credit card fraud detection. Let's say you have a bunch of purchases and someone decides to make a $2,000 purchase to buy like a sound system that you probably didn't buy. So that's also a type classification as well, detecting whether or not there's certain fraud that happened on a credit card. All right, so credit card transactions. Oops. Right, so fraud, non-fraud. Oopsie. Okay, and last but not least, tumor classification if you get into biomedical. Right, there's benign and malignant tumors. Okay, so this is probably the more useful aspect of machine learning that's used often in practice. Okay, so spam or non-spam, credit card transactions, tumors, and so on. Okay. So usually when we take a look at classification, there's yes or no, 0 or 1. So we usually group those responses or those inputs that fall into the yes or 1 or spam category as the positive class. Anything that doesn't belong, 0 or negative or non-spam belongs to the negative class. So there's the positive class and the negative class. That's how we differentiate between the two. And that's the vocabulary that is often used when you talk about classification. All right, so, machine learning, vocabulary. Okay, the yes, one, spam, etc. is the positive class. Okay, it's what's known as the positive class. Okay, and then the no, zero, non-spam, etc. is the negative class. So there's the positive class and then the negative class. It's another, another type of vocabulary that is used. So positive class, negative class, and so on. Okay, so usually when you take a look at classification, your prediction model, the output is usually continuous valued. So your objective is to set some sort of boundary, some sort of threshold, where anything bigger than this threshold means that it's a yes, anything less than this threshold means that it's a no. So the output of the prediction model is usually continuous value, so you got to figure out what the right boundary is to figure out whether or not it's a yes or a no. All right, so the output of the prediction model is usually continuous valued. It helps make finding the minima of the cost function and differentiating easier. So it's continuous valued. Okay, so what you have to do is usually set a threshold, and anything bigger is yes and anything less than is no. Okay, so we need to set a threshold. On where, let's see, threshold, set a threshold on, I guess, where we denote the transition between positive and negative. All right? Positive and negative. Okay, that's great. So I talked about what logistic regression, well, I gave you a little buzzword, logistic regression. That's just a special case of classification where the prediction only lies between 0 and 1. There's possible classification applications where it could be less than 0 or greater than 1, but logistic regression is a special case where it's only confined between 0 and 1. It actually makes analysis a lot easier. So it's not really regression, actually. It's a classification kind of deal, but logistic regression is a term that's been used for historical reasons. Regression you're using to predict, outcomes, right? So logistic regression is just a matter of classification. So it's just a matter of just for historical use. So logistic regression is a special case where the prediction model has the output confined to, so between 0 and 1. So h of theta x is your hypothesis or your prediction model. Right? So that's a special case. And we'll talk about how to interpret this later. So in general, classification prediction models can give, values that are, less than 0 or values that are greater than 1. It depends on which ones you use, but we'll just stick with logistic regression for now because it's an easier one to take a look at. All right? So for logistic regression, because it's between 0 and 1, you usually set the thresholds we write at 0.5. So if you take your, example, if you take your data that has a bunch of features and you put it through the logistic regression model, anything bigger than 0.5 you consider to be the positive class, and anything less than 0.5 you consider to be the negative. So 0.5 is right where the transition should be. Okay, so for logistic regression, okay, so let's see here. Usually, if the output of your prediction is bigger than 0.5, predict positive. Okay, and if it's less than 0.5, predict negative. Okay, that's pretty good. So that's where the threshold is, it's 0.5. So this little guy here is our threshold. All right? So the hypothesis, or the prediction model that is used in classification, it's based on the function which is called the sigmoid function, or the logistic function, or the logit function. You'll see that a lot. It's known by a lot of different terms, a lot of different names, so I'm just going to spit them all out. Okay? So the hypothesis used in logistic regression is it's either the sigmoid function, the logistic function. They're all the same name, or logit function. They're all the same. They're all the same name. So if you read, certain machine learning or pattern classification textbook, when they say sigmoid or logistic or logit, they all mean the same function. All right? So the sigmoid function is defined as the following. Sigmoid. So you have function g, and then the input is z. It's 1 over 1 plus e to the power minus z. Okay, so this is what the sigmoid function looks like. And it has some pretty special properties, mainly because if you make z very, very large in the negative direction, you'll have 1 over a very large number, which makes it approach 0. And if you make z approach a very large positive number, 1 over a very large negative number will make it 1 over 0. It'll make it go to infinity. And then finally, right when z is equal to 0, you have 1 over 2, which is 0.5. So that's pretty cool. Okay, so probably said that wrong, but I'm just going to, so as z approaches minus infinity, right, the output is going to be 0, which makes sense. Okay, cool. All right. As z approaches positive infinity, yeah, sorry, I did say that wrong. So if I approach positive infinity, what's going to happen is that exponential term becomes very negligible. Then you have 1 over 1, which is just equal to 1. And then finally, there's a very special property where when you set z equal to 0, right, well, the output is just 0.5, which makes sense because if you substitute 0 over here, it becomes 1, so 1 over 1 plus 1 is 2, and that's 0.5. Okay. Okay. And what's special is that the domain spans between minus infinity to infinity, and the range is just between 0 and 1, which is nice. It's suitable for logistic regression because we only want it to be confined within this range. Okay, so what does it look like? So it looks like this. Okay, so we have 0.5 here, we have 1, sorry, 1, 0, and it kind of looks like this. So there's an asymptote of 1. It kind of looks like this. Looks like that. All right. So that's what the output looks like. It's nice because this is a function that's differentiable. So the derivative does exist at all points. So it makes it nice when you're talking about cost function minimization and all that. Okay. All right. So that's what the sigmoid looks like. So 1 as it goes to the right, 0 as it goes to the left, and then right at 0, it's about 0.5. So that's what's known as the sigmoid function or the logistic function and so on. Okay, so let's go back to linear regression for a bit. Recall, let's see, linear regression hypothesis. So the prediction model we had for linear regression was just a sum of weights, right? It was, so let me see here. Okay, so it was, theta 0 plus theta 1 x 1 plus, right? Okay, cool. Okay, so, and then you can also represent it as a weighted sum, right? So this is I equals 0 to n, and then with the convention that x of 0 is 1, okay? Or you can also represent this as a dot product, okay? So if you can represent the vector, well, the parameters as a vector of n plus 1, and then the same thing as the vector of x, you can represent this as a dot product. So Okay, okay? And then the vector is going from theta 0, theta 1 down to n. And then this one is also a column vector, but with the notion that the first element is 1. Okay. So the only difference between logistic regression and linear regression is that you're still using the same hypothesis, you're still using a weighted sum, but what you're doing is you're taking the output of this and applying the sigmoid function to it, so that you're binding the output of this so that it goes between 0 and 1. That's really the only difference. All right, so logistic regression. Oopsie, sorry. Simply takes the, sorry, not the, but we'll take the prediction model and applies the logistic function to it, or sigmoid function to it. Sigmoid function to it. Okay, so it's seriously just this. So remember the sigma was g. So all you're doing is you're just taking the linear regression or the linear regression output and just applying a logistic function to it, or the sigmoid function to it. So it's simply this. Okay. And this was just the weighted sum, this guy over here. So you only have to do one piece of extra work. So first compute your linear regression output, and then take that and apply the sigmoid function to it. So you're bounding it between 0 and 1. That's really the only difference. Okay? Okay. So, this is all nice and cool. So how do I interpret this hypothesis? What does it actually mean? So when you take a look at the output of this prediction model, what it's telling you is the probability or the chance of success that the input that you're putting in belongs to the positive class. So the probability that this instance that you're providing to this model belongs to the positive class. That's how you can interpret the hypothesis in this case. All right? So how do we interpret? How do we interpret that? Okay, so this is the, I'm sure this was a word you never wanted to hear again, but unfortunately we're going to have to cover a little bit in this course. To be honest, when I took this course I hated this crap too, but we're going to have to unfortunately cover it here. This is the probability that we classify input x to belong to the positive class. Okay, so that's how you can interpret the output of this prediction model, because it goes between 0 and 1. Okay, so just a brief definition of probability if you don't quite remember what it is. So probability is basically the likelihood or the chance that you'll take on a particular, or the chance that something is going to happen or some event's going to happen. Okay, so probability is, let's see here, it's the chance that something is going to happen, all right? Okay, so it's bounded between 0 and 1, so between 0 and 1, so if it's 0, then it's not going to happen. There's no way in hell. And then if it's 1, then it's it's going to happen whether you like it or not. Okay, so just a quick example. Let's say X was the tumor size, all right? And you're trying to figure out whether or not a tumor is benign or malignant. So if I decided to put this into a prediction model and then I got the output as being 0.7, this is saying that if given a particular tumor size, if I get an output of 0.7, this means that there's a 70% chance or 0.7 probability that the tumor is malignant, which belongs to the positive class, all right? So if this means there is a 70% chance that the tumor is malignant or belongs to the positive class. Okay, a positive class. Okay, cool. Okay. Also, if there's a 70% chance that it's malignant, then it makes sense to say that there's a 30% chance that it's not malignant or it's benign, right? Because all the probabilities sum to 100%, so you want to subtract from 70, you get 30 to get the other outcome, right? And then also, this tells us that there is a 30% chance tumor is benign or belongs to the negative class. Usually the positive class means that there's a presence of something, and negative class means that there's an absence of something. So that's how I usually differentiate between the two, but it's just notation. As long as you're consistent, we're okay. Okay. So just a little example there. So what we're going to do is I'm just going to introduce a variable called y. So y will either take the value of 0 or 1. So 0 meaning that it's negative, or 1 meaning that it's positive. Okay, so just to, instead of me writing a positive and negative class, I'll just say y is equal to 0 or y is equal to 1, just to make writing a little easier. Okay, so let y represent the class. Okay, so if y is equal to 0, this means that it's a negative class. Okay, and y is equal to 1, this is the positive class. Just make life a little easier because I don't want to keep writing positive or negative class and so on. Okay, so therefore the hypothesis, okay, the output of this logistic regression model is the probability that the class of the input is 1, right, given x and then parameterized by theta. So that's what this is. Okay, so how you can interpret the statement is that the output of your prediction model is the probability that the class is positive. Okay, and this little vertical pipe here means given, and then these guys right here, given the input x parameterized by theta. So what parameterized means is that this probability is heavily dependent on what the parameters are, right? So if your parameters are incorrect, then their probability is going to be incorrect as well because it relies on the correct parameters. So if you don't have the correct ones, then even though, you know, it'll give you a probability measure, it's not going to be correct because it's parameterized by those. So it's heavily dependent on the parameters that you learn as well. So what parameterized means is that it's heavily dependent on theta, okay? Also, just for the sake of completeness, if you wanted to predict whether the particular input belongs to the negative class, it's fair to say that you just subtract 1 from this. Makes sense, right? Because if the tumor, there's a 70% chance that it's tumor, if you want to predict that it's in the negative class, just do 1 subtract, which makes sense because the law of total probability says that the sum of all events is equal to 1. So 1 subtract is, is a fair thing, fair assessment to make. Okay. So instead of having having 2 separate equations, what we can do is we can combine this into 1 equation to make our analysis a little easier. Okay. So we can combine both statements into 1. Okay, so it's safely fair to say that we can actually do this. So we can say that the probability of the class y given the input and the parameters, parameterized, it's simply this. Okay? And you stare at it for a minute, it kind of makes sense because if if y was the positive class, I mean if y is equal to 1, then the second term will just cancel out, it becomes 1, and then you're left with just the left side. If the negative class happens, then the left term becomes 0, so that becomes 1, and then all you're left is the right side. So it actually combines both of them together, which is nice. So let me just write that out. So if y is equal to 1, well, what's going to happen? If y is equal to 1, then the right term, 1 minus 1 is 0, and then anything to the power of 0 is 1. So anything you're left with, everything you're left with is just the left-hand side. If y is equal to 1, then you're just left with this. Okay, that's great. And if y is equal to 0, the left term goes away, and then all you're left with is the right, and then you just get that as well. Okay, great. Now the reason why I'm doing this is because it's going to lead on to how we find the right parameters for logistic regression, the right parameters used to predict different classes. That's why I'm doing this. Okay, so what we're going to do now is I'm going to define a term which is called the likelihood. Okay, so likelihood is a term that you may have seen in probability, but I'm going to redefine it here. So what the likelihood means is that it's the probability that the parameters that you've found fit the data. So the higher the probability, the higher the likelihood, the more likely the parameters that you found will fit that data well. Okay, so that's what the likelihood means. So let's see here. Okay, so now define the likelihood. And I'm going to call it L of theta. Okay, so likelihood means it's, let's see. So let's now define the likelihood. All right, so, okay, so this is defined as, maybe I'll skip over and do this, as the probability that the parameters best fit the data. Okay, so so given, so let's say we got a few training examples to take a look at. This is part of your training data set. Okay, so they're usually accompanied by by points in a label. So x2, y2. This is just convention from before, right? Okay, so this is input point. I guess you can call it point, and then this is an output label or expected label. And remember, we're only dealing with binary for now, so this is either 0 or 1. Okay, so we've got M training examples, and then how we define the likelihood is very simple. But before I do that, I gotta just cover one little thing before I carry on. Okay, so what we're gonna do is we're going to assume that this is an experiment. So when you're collecting training samples, we're going to assume that every single example is independent of each other. So what does independence mean? It means that in no way that you collect one sample does it depend on any other sample. So they're all independently sampled. So if you grab one, it doesn't rely on you grabbing another one. So taking your training examples, they're all independent. Okay, so assume we grab the M training examples independently. Okay, so recall what independence was, and I'll cover this a little more when we actually talk about probability later. I'm going to do a little bit of a review just to make sure that everyone's on track. But independence means that two events or two situations or two events are independent if the probability of one event can't write today, of one event doesn't affect the other. Affect another event. So a good example of independence would be flipping a coin or rolling a die, assuming that the die is fair-sided. You're not warping any of the sides, or the coin is fair. So every time you do an event, it doesn't correlate or it doesn't affect any of the outcomes before or any of the outcomes after it. Okay. So examples would be flipping a coin or tossing a die, assuming that it's a fair die or fair coin. Okay. Okay. So the main definition is given two events, A and B. When you want to find the probability that they both happen at the same time is just multiplying them together, which is great. Okay? All right. So that's the main point I wanted to drive home. So how does this work for our likelihood? Well, if we assume that, the M training examples, okay, are independently sampled, then what you can do is you can find the probability that you get all of them together, how they all occur at once, by just taking each individual, hypothesis for each sample and just multiplying them all together. So that would be the likelihood for all of them that you encounter given your parameters. Okay? So the likelihood of the parameters is, taking the first one, okay, multiplying it by the second one. Whoops, sorry, I can't write today. And then you keep multiplying, and then we have the last one. Okay, that's great. Okay, just to be concrete, I'm going to represent this as a product. So sigma is the sum, right? And pi, the capital pi, means the product. So going from 1 to m training examples. Okay, so that's what the likelihood is defined as. Okay, that's cool. All right. So the goal of this is to figure out the parameters that will maximize the likelihood. This is what's known as a maximum likelihood estimator, is you want to find the parameters that will give you the best possible probability that fit the data well, given those parameters. Okay? So the goal is to maximize the likelihood. It's what's known as a maximum likelihood estimator, but we'll talk about that later. Okay, maximize the likelihood. All right, so we want to find the parameters that give the highest chance or the highest probability or the highest success rate to fit the training data. So that's how we're going to approach in classification. So with regression, you had a bunch of points and you want to fit a straight line through as many points as you can. That's the point of regression. Okay? The classification is a little different. You want to find the parameters that best match all the points in your data set with the highest probability possible of matching. Okay, so it's slightly different, but they're completely different. They're completely different meanings. Okay? So instead of dealing with products, what I'm going to do is I'm going to take the log of this function, because when you take the log of a bunch of products, it's the same as adding everything together. So dealing with summations is much easier to deal with than dealing with products. All right? So it is easier to deal with the log likelihood. Okay? So what I mean by log, okay, is actually ln. So log is the ln function, or log to the base e. Okay? So that's what I mean by log in this case. If you actually take a look at many different textbooks, when they say log, they actually mean log to the base e, just to make sure that it's not ambiguous on what base what base you're considering. Okay, so the reason why you deal with log is because it removes the power operations. So, it makes it a lot simpler to deal with. I'd rather deal with a sum than a product of multiples. Okay, so the product. So what I'm gonna define is small case L, which is the log of the likelihood. Okay. Okay. So small case L is the log likelihood, and capital L is just the likelihood. Okay. So the product becomes now. So what's going to happen is that this becomes log of this entire thing, right? Because we're taking the log likelihood. Okay. So if you remember from properties of log, if you take the logarithm of two numbers that are multiplied together, it's the same thing as splitting them up with the same base and just adding them instead. Okay, so this is naturally represented as a product of components. So if I take the log of a bunch of products, it's the same thing as summing them all together. All right, so this is the same thing as log, and then you have the first one. Sorry. Okay, plus the second one, and so on. Okay. Okay, and then I'm just going to represent this concretely as a summation instead. Okay, so log. Okay. And then let's see here. And if you remember from before, this probability of this thing, it's represented as that complex measure that we had before. So this is equal to what? This was h of theta. This is y, and then times 1 minus theta, 1 minus y. Okay, so you got that here. Yep. Okay. So now there's a little more we have to deal with. So if you take a look, we have a product of two terms. So we're going to split this up a little more. Okay. And then let's see here. Okay, so we have this. And then we also have, when you take the log of the power, so let's say you've got log and then a to the power b. This is the same thing as taking this power and bringing it down here. So this is b log a. Okay, so I'm going to do that instead. Okay, and then we have a product of two terms here. We can just split this up. So in this case, what's going to happen is this becomes, so we have y log, okay, and we're using the same thing as before. This is yi, sorry, and then, sorry, I forgot the x of I here, because we're dealing with many training examples. And then 1, and then 1, and 1. Okay. All right. I think I got that. Yes. Okay, and that's the final one. Okay, this is the likelihood. That's great. Okay, so what do we do with this? So we seek to maximize the log likelihood. Okay? So we seek to maximize this. So find theta such that, you know, it maximizes that. Okay? So how? How can we do this? Well, if you remember from gradient descent, the point of gradient descent is to minimize something, is to minimize cost functions. So what we can do here is we can take this likelihood and we can convert it into a cost function if you wish. And there's a little bit of a trick that I'm going to show you in order to do that. So how can we do this? How can we do this? So let's see. How do we do this? So recall gradient descent. Okay, this was used to minimize cost functions. Okay, so we can convert this, well, we can convert the likelihood into a cost function. How do we do that? So what you do is you minimize the negative of the log likelihood. Okay? So if you think about it, if you want to find the maximum of a function, it's the same thing as minimizing the negative. Okay? Think about that for a minute, because let's say the maximum point of a function was 10,000. Okay? If you try to minimize the negative, it's going to find the smallest possible negative number that will minimize that function. So the minimum is going to be, if you decide to put a negative on the function, it'll give you minus 10,000 as the minimum. And then if you negate the output, it'll give you the maximum. So if you minimize the negative of a function, it's the same thing as maximizing the function. Okay, so all you have to do is just slap a negative in front of the likelihood, and that changes it into a cost function. All right? So let's see what we got here. Okay. we can convert this, minimize the negative, okay? So what we mean to do is, therefore, the cost is just slapping a negative in front, okay? And then what I'm going to do is I'm going to also put a 1 over m here, because what we want to do is we want to find, this turns into a cost function, so this actually evaluates the error that it's going to take in order to take your parameters and make them fit the data the best. So in order to make this meaningful, I'm going to divide by 1 over m, which means that this is the average error that it will take if you decide to use those parameters to fit the data as best as possible. All right, so this is the negative here, and then makes, finds the average error. Okay, so therefore, if you want to minimize the cost, it's the same thing as maximizing the likelihood. It's the same thing. Okay, just a little trick that you can use, because there are some functions, or there's some tools out there where it only allows you to find the minimum. It's like it's what's known as a function minimizer. So it only allows you to find the minimum of a function. So if you want to find the maximum, you just turn the function to a negative and then find what that minimum of that negative function would be, so you get the maximum instead. Okay, so let me just write this out and then take a little bit of a break after. Okay, so therefore, the cost function is now minus 1 over m. And then I'll carry the minus m, so minus 1 over m, sorry. So this is 1 over m, summation. And then I'm going to carry all the negatives inside, because I don't like the, just for convention's sake. Okay, and then plus or minus. Okay, so this is our cost function. Right, it's a little different, but it's not so bad. Let me just make a couple of points before I take a break. Okay, so that's great. All right, so this is what's known as a maximum likelihood estimator. Or MLE for short. You'll see that a lot. You see this terminology a lot if you decide to read some machine learning textbooks. So maximum likelihood estimators to find the parameters that will maximize the likelihood that those parameters will fit your data as best as possible. Okay, so let me just write a couple more notes and we'll take a break. So how does this work? How does this cost function work? Why is it so special? Okay, well, what we're going to do is I'm just going to consider one example for now. So let's just assume that m is equal to 1 for now. So I can show you what it looks like. So let's assume m is equal to 1. Okay, so if y is equal to 1, right? So actually, let me just write out the cost function. So if it's just m is equal to 1, so I just have just this, right? So log of h theta x, and then minus, sorry, let me just carry this over. Running out of room. Just want to show you just the intuition with this, and then we'll take a break. Okay, so this is just for one example. All right, so if y is equal to 1, what's going to happen? Well, if y is equal to 1, then the second term goes away, and all we're left with is the first term. So in this case, this is just, the cost is just equal to minus log of h of theta. Okay? So what this looks like is that it looks like this. Okay, it kind of looks like this if you plot it out. So this is minus log of h theta x. Okay? Remember, this is between 0 and 1. Okay, so what does this mean? Well, you know that the hypothesis is between 0 and 1, okay? So if h of theta x is equal to 1, so this is saying that if the hypothesis, if the output of the hypothesis, if that's equal to 1, that means that we made the correct guess. So the predicted class is 1, then the output class is also 1. So when you actually compute this term, the log, it should give you 0, right? So if h of theta is equal to 1, therefore the cost should give you 0, because log of 1 will give you 0. So this means that the predicted output gave you the positive class, and the true output is positive as well. So because they both agreed, it should cost you nothing. There's no cost associated with the true predicted output, which is 1, and the predicted output from your prediction model, which is 1. So they both match, which means that there's no cost, right? So no cost incurred because prediction model made a correct guess. Okay, that's good. But if h of theta is 0, what'll happen is that we made the output, the true output is 1, but when you take log of a very small number, negative log, it's going to shoot to infinity, which means that the true class is 1, but the prediction model is classifying it as a 0. So that means that you're going to assign a very high cost, because you're telling the user that the prediction model is the other class, even though the true class is 1. You're telling me that the actual class is 0. So you want to make sure the cost is very high, because that's not the right output. So you got to make sure that cost is very high to penalize the user for classifying it that way. Okay, so if h theta is 0, so what this means is that we're going to choose the other class. So choose the other class. And right, so let's see here, it's going to be a very large number. Since, h of theta is approaching 0, okay? And then therefore, high costs incurred. Okay? Okay, I guess due to wrong prediction. Okay, I'm just going to make a very similar observation with the other one, and then we'll take a break. So if, I'm just going to write this down quickly. If, y is equal to 0, similar observations can be made. Okay, so in this case, so if y is equal to 0, the cost, it's going to look like, what is it? It was log of 1 minus. Okay, and it looks something like this. Something like that, so something close to that. Okay, so this is log of, and this is minus, I believe. Sorry, this is a minus, because of that sign on the outside. Okay, so it looks like this, and then the same thing happens. All right, so if h of theta x is equal to 0, we made a correct guess. So no costs incurred. Right? Because if h of theta, if the guess is 0, then what's going to happen is this becomes minus log of 1 minus 0, and that becomes 0. Okay? And then similarly, if we predict the wrong class, okay, we need a high cost to assign the input x to the other class, right? Because we predicted the negative class, but the prediction output is giving you a positive class instead. So it's going to give you a high cost, right? So that's what that looks like. Therefore, will be very large. Okay? So the whole point of this cost function is to penalize wrong guesses and reward correct guesses. That's the whole point of this cost function. Okay? All right, so I'm going to stop here. We'll take a little bit of a break. We come back and we'll continue on with this stuff.